This video introduces the multiple linear regression model. Before we get into this, let me mention that the best way to understand multiple linear regression is to have a real thorough understanding of simple linear regression. So if you really understand simple linear regression, it's not that bad of it's not that hard to make the leap to multiple. So you should make sure that you've completely mastered simple linear regression before tackling this. So the main difference between simple linear regression and multiple linear regression is that you have multiple predictor variables. So with simple linear regression, you had exactly one predictor. With multiple regression, we're going to now allow for p predictors. We've already seen an example of this last time when we talked about the Click Ballpoint Pens Company. So recall, with the Click Ballpoint Pens Company, we had three factors that we thought caused sales. So advertising, number of sales reps, and the wholesaler efficiency. So that would be p equal to 3 predictor variables, and we're going to use those to predict the dependent variable, which was sales. So let's look at the multiple regression model. So this is the model, and if we start with the part that I've highlighted, we start with the simple linear regression model, so this plus the errors. So the only difference between this chapter and the previous chapter on simple linear regression is that now we have an additional set of predictors in the model. Now, let's review slightly what this model said. So the model said that the recipe for generating these y's is that we have some line, that's this beta naught plus x times beta 1, and then there's some error. So I'm going to bring up a graph that we generated at the with the machine example. And so we had the cost of a machine and the age of a machine, and here is that line. So that is, beta naught plus age times beta 1, and the red triangles represent the points on the line. Now, where did the observed y's come from? Well, those circles are just the points in the line plus some error. So do you see how we've gone from the line to these points by adding those errors? So the black lines represent those e's. Now, the other thing to recall about last time is that the expected value of y, so in this case the expected cost given a certain age, so let's say we have a machine that's 3 years old, well, the expected cost is going to be the point on that line. So we have a normal distribution around this. The point on the line is the mean. All right, so the only difference now is that instead of having one predictor, we're going to have p predictors. So if we had two predictors in the model, then instead of having the means described by a line, they would be described by a plane. If we had 3 or more, then it'd be a hyperplane. All right, now let's move on to actually estimating this model. So in real life, we don't know the values of these parameters. So the parameters being all the slopes and then the standard deviation of those errors. Instead, we observe individual observations, and we have to estimate them from data. Well, the way we estimate them is going to be almost identical to what we did before. We just have more predictors. So I'm going to now use this diagram to discuss the estimated model. So the y-hats are fitted values. Those are those red triangles in this line. And so, if we had one predictor, it would be a line. The black lines describe the errors. So we call those e-hats or residuals. And that's just how far is y from y-hat. So the black circles are y's. The red triangles are y-hats. So the difference between that is the length of the residual. So this observation has a positive residual. This observation would have a negative residual. Okay, so now we're going to choose the line. So what makes a good line, or in this case plane? We're going to choose it to minimize those errors. So it's the exact same objective function. and I've written it in some matrix notation over here. How do we find those? Well, how do we find the estimates? We differentiate with respect to b, set it equal to 0, and then solve for b, and you get this a very famous equation. So these are the least squares estimates of the regression coefficients. Now, we had a very similar slide back when we talked about simple linear regression, and this is completely analogous to that. So the expected value of b is beta. These have normal distributions, and we have our ANOVA table from last time. So all of this is almost identical to what we had last time. I'll now give you a process that you should use in building multiple regression models. So the first thing that you want to do is identify a good model to estimate. We're going to talk more about that in future lectures next week. But let's say that we've got a decent model. We know we have a pretty good idea of what predictors we need to explain the dependent variable. We know how they relate to y. We just need to estimate the coefficients. So if that's the case, then what we're going to begin by doing is inspecting our data for outliers, any problems with the data. So I would definitely do the following, generate some descriptive statistics, make sure the minimum and maximum values make sense. So if you have a 5-point scale, all the values should be between 1 and 5. Probably want to look at some box plots of the data, and the box plots should not be horribly skewed with outliers. If they are, you're probably going to need to transform them, as we'll discuss next time. You should probably look at a scatter plot matrix as long as the data set isn't huge. Don't try this with 1,000 points, but if you have 100 points or a couple hundred points, a scatter plot matrix will also show where there are issues. You should also look at a correlation matrix for reasons that we'll discuss next week. We want to find out how the predictors relate to each other, as well as how each predictor relates to the dependent variable. Then you want to estimate the model. We want to check for normality. We'll discuss checking normality next time. Then what we're going to do is an overall test of significance. So this is, I call it a screening hypothesis. So we're going to test whether all the slopes are simultaneously 0 against an alternative that at least one is non-zero. And if you can reject the null hypothesis that they're all 0, then you go look and interpret individual coefficients. If you can't, you should just stop. So I'm going to, in a minute, do a few examples that illustrate this process and the meaning of all these terms.